So let me start by thanking the organizers for inviting me here to this workshop and to this beautiful ICTS campus, and giving me the opportunity to talk about this topic, physics in Charm Radiative Decays. All right, so this is the outline of my talk. I'll start with some motivation and then discuss the issue of short distance versus long distance effects. This was dwelled upon in the context of Meson decays yesterday in Ambrosius' talk. And then I'll go on to discuss the QCD enhancement in the standard model, as well as in a model with down-type vector like quark. I will then add a left-right symmetry to the model, and that will basically help me come up with an observable, the polarization of the photon, which can help to pin down new physics. And I will, of course, long-distance effects are present, so we have to deal with them, and I will point out next how we estimate them. And finally, I'll have the results, including the polarization of the photon, as well as the branching ratios. Okay. So why do I want to look at charm decays? I mean, we know charm is neither heavy enough to use heavy quark effective theory, nor is it light enough to use chiral perturbation theory. So calculations are hard, then why would I want to do this? Well, basically, direct search for ESM has been unsuccessful so far, and we have heard about some anomalies in the flavor sector in the last few days. Rare charm decays provide a path for new physics searches, and so we need to look at all possible avenues. And charm could be one such avenue, as Zoltan Legety said in his CKM workshop summary talk, that we should not leave any stone to also pin down the model of new physics. And if you're finding, get a framework which is able to explain many, many anomalies, then you can believe that you have found you can pin down the new model of physics. In fact, John has been talking about symmetry and how it explains many, many things. So that's the idea. And you have to look for, you have to try to come up with various possible anomalies or new physics signals, and also all of them can be explained in one framework that hopefully can help us pin down the model of new physics. Okay, so now let me mention about short distance versus long distance effects. While in the case of the mesons, the short distance effects dominate, the charm quark decay systems are dominated by the long distance QCD contributions. Of course, okay, in the meson systems also you do have some long distance effects, but you can basically club them into small factors and get away with that. Within the standard model, the short distance in charm decays suffer from almost complete, because if you look at the diagram for C2 gamma, which is the radiative decay I'm talking about here today. Yeah. So what I was mentioning was about these loop diagrams for the C2 U gamma. What you have in the internal quarks are the down-type quarks, the D and SP, which are all light, almost massless compared to the electroweak scale. And that's the reason that, this contribution within the standard model without QCD correction is very, very tiny. Okay. And particularly if I want to look for new physics, which is, coming in these virtual loops, some other virtual particle comes in these loops, then I have to make sure that the long distance effects don't screen the presence of this new physics particles that may appear in that loop. Okay? So basically, the new physics short distance enhancement should be larger than the long distance contributions to be distinguishable. Alternately, I could look for special observables, and one of the proposals had been to measure the difference in the rates of the exclusive modes d2 rho gamma and d2 omega gamma, in which the long distance effects are expected to cancel. This was done by Pfaffer et al. Many years ago. And so they said that that would indicate short distance new physics if the data reveals a difference of rates which is more than 30%. We will demonstrate that the measurement of the photon polarization, the photon emitted in this decay, can be used to signal new physics. And we'll explore the effects of the presence of a heavy vector-like down-type quark, isosinglet quark with additional left-right symmetry. And since we have only an isosinglet down-type vector-like quark, usually you would have these ZFCNCs coming from the vector-like to quark, but then those FCNC will come in the down-type sector, will not affect further, will change our C2U gamma. So that's one of the motivations to look at isosinglets here. Okay. So how do I enhance the rates? As I said, in standard model at the bare level, because the branching ratio is very, very small. Well, within the standard model, there's an enhancement of the radiative decay rates in terms of QCD corrections. In fact, even in B2S gamma, you get a correction of about a factor of 2. But a more dramatic enhancement is expected in the case of Charm Radiative Decays. And hence, we need to evaluate the corresponding Wilson coefficients with the RG improved perturbation theory. And of course, you can get enhancement also with new physics, and that's what we want to do. Need to enhance the rate above that from the long distance effects, or as I mentioned in this slide before, need to find signals that can be observed even in the presence of the long distance effects. Okay. So regarding the short distance contribution in the standard model, this is the Lagrangian. I've neglected the term proportional to mu. And of course, these are your standard loop functions, the Namaline functions or the modified King-Tham functions, where you will be summing over your internal quarks DSP. So, and it was shown by these people many years ago that there is an enhancement from order 10 to the power minus 17 to 10 to the power minus 8 of the branching ratio with next to leading order corrections. But that was a calculation a long back, so we just repeated that, and we do get the large enhancement. Basically, when you're doing the QCD corrections, you will write down first the Hamiltonian for the scale between MW and B. You start integrating out the weak gauge, W gauge bosons, and at that point, basically, since you're summing, your P quark is present, you're summing over these, all the three, and all you get is these current operators, the C1 and C2 contributions only come. You do not get contributions that from the other operators, the O3 to O10, because of unitarity. You're summing over all of them, and if there's no dependence on the specific quarks, this sum over all the three quarks from unitarity just goes to 0. So then, of course, once so you start with the W scale, you do the matching of the full effective theory to the 5-flavor theory, and then you do your RG evolution, you run down to the B scale, and once you come to the MB, then of course you have to match the 5-flavor theory to the 4-flavor theory and integrate out the B quark now. So once the B quark is integrated out, of course I can have these additional operators. So that's at the stage at which your C7 and C8 can contribute to O7 or A8, which will be basically the O7 is what I need to enhance my radiative decay. Okay. Yeah. I'm talking about C2U gamma. U gamma, the inclusive C2U gamma. Yeah. All right. So now, apart from the standard model, we looked at the vector-like down-type isosinglet quark, which I just mentioned a few minutes ago. And the possibility of the short distance enhancement with this kind of a model had actually been mentioned. I was not aware until we started working by Babu, K, Lee, and Pakasa many, many years ago. And the advantage here is that you have no new operators introduced for this transition. But the important point is that now above the B scale, one needs to integrate out the B prime also. So your B prime is very heavy, about 800 or 1200 GeV. And when you integrate that out, and it's above the B scale, basically now, as I said earlier, your 07, 08 do not contribute above the B scale. But now you have this B prime, so you get contributions to 07, 08 as well, in presence of this B prime quark. Chi-square fit to many flavor observables was performed to obtain the central values of all the elements of the measurable, this 3×4 mixing matrix that you'll have in presence of this down-type vector-like quark. This had been done by, I think I have the reference, right? By Alok Banerjee, Kumar, and Shankar. So they considered all possible V observables, BV bar mixing, KA bar mixing, K star LL, and so on and so forth. A huge number, a whole set of observables. And then from that, they try to deduce what are the allowed ranges for the vector-like singlet quark, the mass as well as its mixing angles. So we use their fits for our numerical work. Okay. And as I said, we do the RG evolution and calculate the Wilson coefficients. As you notice here, basically whether I have standard model or I have a B prime of 800 or 1200 GeV, C1 to C6, there will be no change, right? There's no mixing of the dimension 6 operators with the C7 and C8. So it's only at this point that this changes, that you have this, because now your presence of B prime means I have my C7 and C8 present, which was absent in the standard model. So other ones don't come from the same. So let me go on to show you the branching ratios. So the branching ratios, if you see here, basically my standard model, when I look at the bare calculation, the branching ratio is really very, very tiny, of the order of 10 to the power minus 17. At leading order, there's only an increase of 2 orders, by 2 orders, and at the next one, then you have a much more bigger enhancement. And this is actually not because I'll not, maybe if you have time, I'll not go back to the table and show you. It's not that the C7 effective is getting so much enhanced, it's the CKM elements that are coming in here. In this case, that's why the enhancement is much more at the NLO low level than at the LO level. So, okay, that's, as I said, we also add a left-right symmetry to this model. And the idea is then I can have access to polarization of the photon. Vector-like quark, while it's vector-like, so it's not just, it has both left-handed, left-handed and right-handed possibility. I mean, it's, but by itself, since I have an isosinglet, it's not going to help me in my polarization. So I need to have a left-right model where I can get contributions from the left and right currents. Okay. So this is, of course, the standard left-right symmetric model. You all know is based on this gauge group. And now to ensure perturbative interactions between the right-handed gauge boson and the fermions, zeta G, which is the ratio of the right-handed to the left-handed coupling, should not be too large. And direct searches, in fact, impose the bound on this product, zeta G times the mass of this W2, that should be greater than 2.5 TeV. Also, your VR should be in the range of TeV range if you're using seesaw for your masses of the neutrinos. And these constraints basically imply that my zeta G should lie between 0 and your zeta G is GR by GL, yes. So the smaller GR seems to give, is giving, this is
Okay,
Yeah.
Tripondo, let us ask these
Yeah,
questions after that.
yeah.
Okay.
Okay. All right. So the charge gauge bosons, of course, WL, WR are mixtures of these W1, W2 with a mixing angle zeta, which again is restricted to lie in a certain range, 0 or -3. And since the minimal left-right symmetric models are becoming harder to realize, we use a right-handed mixing matrix, which is distinct from the left-handed CKM matrix. Many people tend to just take the left-handed CKM to be the same as the right-handed, and you see it, but we take it to be distinct. Of course, to restrict our parameters, we just take this form for the right-handed mixing matrix. For this 3×3 case, I'll come further to the case when we have an additional vector-like quark. So this is now my left-right contribution. I'll not go into all the details, but just basically point out. So in addition to your left-left terms and the right-right terms, you have the LR terms and so on and so forth. And you have this A piece and B piece. So basically, you'll have both the left-handed and the right-handed contributions. And your photon can therefore be right-handed as well. Okay. So now, these are the additional parameters that I have when I have a vector-like quark and the left-right symmetry. So for the left-right symmetry, we have that zeta, the mixing angle, the zeta g, the ratio of the couplings, and this phi1,2, which was parameterizing my right-handed mixing matrix. And then I have, when I've added a vector-like quark, I have this mass, and it's theta angles. These theta angles are the additional angles, the 1, 4, 2, 4, 3, 4, etc. But then I also have my phi I4, which are for the right-handed mixing matrix. I seem to have missed showing you one of the tables, but maybe I can skip. Oh, okay, I did. So the thetas were the values that were there in the table, which was from the fits of Umashankar. Anyway, if anybody wants to go back to it later. All right. All right. So, of course, now if I have to talk about the branching ratios and the photon polarization, I have to worry about the long distance contributions. And now these being non-perturbative are, of course, hard to estimate, but they are separated into two classes. The first one corresponds to basically, when you have a D decay, it can decay through annihilation or exchange or tree diagrams. And so if you have annihilation or exchange diagrams, then basically you have this process CQ1 bar going to Q2, Q3 bar, and the photon can be attached to any of the 4 quark lines. But at the hadronic level, what it really means is that it manifests as long-distance pole diagrams. Because in between, before you have a photon, in fact, maybe I should go to that figure first and then point out. And the second contribution is basically the quark processes Q1, C going to Q1, Q2, R2, which is basically like a D decaying into 2 vector mesons, say. Because why vector? Because one of them has to finally convert into photons. So to conserve spin, I want to look at vector-vector. So this, for example, here, and I have this Q2 bar Q going to gamma. And this is what is known as the phenomenological model and procedure of vector meson dominance. Okay. So, yeah. So as far as as I said, these pole contributions are basically coming from annihilation diagrams. I have the D, the quark anti-quark annihilating, and I have some, I go into intermediate some other state, some pseudoscalar meson. I'm going from D to the N through a weak interaction, and then I emit a photon and vector meson through electromagnetic interaction. But the photon could have been emitted first. When I have the photon emitted first, then obviously this state, intermediate state, will have to be a vector meson, and it will be a DN star because I've not had a weak interaction yet, so the C quark remains here. And so these contributions, so it's like essentially getting this one is getting contributions from some pseudoscalar poles, and this is getting contributions from vector poles, and you calculate those contributions. These you call type 1 and type 2. Basically, you have this interaction, the propagator, and this coupling, which you try to determine from experiments. And of course, in the second case, you have the other way around. You have this photon coming first, this coupling coming first, and propagator. Okay. Yeah, sure. Yeah, sure. Yes, yes, yes. Right, right, exactly. Yeah, in fact, here, basically, with the data for the scalar resonance is much scarce, so it's kind of, we, in fact, did that also. We added the scalar as well as, yeah. But generally, people just tend to add this scalar, but definitely both all of these terms, they all have both parity violating and parity conservative contributions. Okay, so, yeah, and in the case of vector Meson dominance, basically you have your D Meson. The D could basically have a transit to another vector Meson V1, and the V2 could be then popping out from vacuum, and that V2 could basically convert into a photon or the other way around. So you use factorization assumption and write down your VND amplitude in terms of form factors, and we here these AIs are basically the A1, A2, the corresponding to the color suppressed, color favored cases, and X is the Meson which finally couples to vacuum, and that's why you have this decay constant of this Meson, and this is the transition of D to this Y, which involves all these form factors, and this kind of form factors we've seen yesterday in Symmetri's talk. That was in context of P decays, but yeah, similar form factors all come in, and these form factors have been calculated by Hoffer et al., and that's what we have used. Okay, so I will go on further. Now about the photon polarization. So within the standard model, in this penguin diagram, obviously you will only have left-handed components of the external photons. Helicity flip on the C quark leg will be proportional to MC, and that contributes to the amplitude formation of left polarized. You do have, if you have a helicity flip on the U quark leg, then you could have right polarized, but then that is highly suppressed, right? You have it will be of order mu by MC. So we then, as I said, we looked at LRSM along with this vector-like quark. And in this LRSM, since the physical W1 couples to both left and right quarks, a helicity flip is also now possible on your internal quark. So earlier you were just looking at the helicity flip on the external legs. Now you can have a helicity, oops, okay. All right. So this is proportional to MB zeta. So as zeta is bigger, you will have more contribution. And the main point I want to point out here is that, and if you have a heavy vector-like quark, then this flip will be proportional to MB prime zeta. And MB prime, as I pointed out, would be, the preferred values are 800 or 1200 GeV. So that makes it much larger. Okay, so so we define the photon polarization for this process like so. Basically, CR, CLB denoting the amplitudes for the right and left polarized photons in the process. Of course, in the standard model, the SD short distance contributions to CR are negligible, and with only short distance contributions, then your lambda gamma would be just -1, right? This is all that you have. However, when you're looking at the exclusive decays, they were dominated by the long distance contributions. So to count for these, you have to add the pole type, VND type of amplitudes for all the exclusive Charm Meson processes to get the sort of inclusive, long distance effect to compare with the short distance, which we have calculated at the inclusive level. And basically, but one has to remember these long distance effects are just coming from your QCD corrections, but non-partitive QCD corrections. They will be can be, the photons coming from there will be equally left and right. So that is the main message here. Basically, long distances are large, but because of the fact that they will contribute equally to the left and right polarized photons, the short distance effect, if it is introducing some polarization, it survives in the presence of these long distance effects. So although there are interference effects, so it's not as simple as that, but that's the basic picture. So, okay, this is just the number that we have here for the long distance amplitudes. And now, as far as the polarization goes, for the standard model case, as I said, this is not there, so this results in photon polarization of the order of 10 to the minus 8 to 10 to the minus 5, so almost 0. So although you would have, you had the left-handed one from the short distance part, but then long distance effects may show that being much larger for the standard model, they have this effect of reducing it to 0. But now, what we did was that we expressed the photon polarization as a function of all these parameters that are there for our left-right model and the vector-like quark model, and then we varied them in their allowed ranges, and then look for the maximum deviation of the polarization from the standard model value. And what we found is that, so this left plot is for left-right symmetric model, but without long-distance effects, just to illustrate the effect of what a mess long-distance effects can make. Here, what we find is that for small values of zeta, zeta g, then that's almost like standard model. Your polarization is -1, and as you have as your zeta and zeta g increase, it becomes +1. So without long distance effect, the picture looks very nice. Once I add long distance effects, of course, and I have only LRSM, then I do go away from 0, but to very small values. The advantage then is of the vector-like quark model seen in these next plots, that here now I have LRSM with 800 GeV or 1200 GeV vector-like quark, and I find that as I'm going to larger and larger values of zeta and zeta g, my polarization can actually go up even to +1. So I have this parameter space where it's going to +1, and in all this region, I'm actually deviating from the standard model value. So polarization does look different from standard model value in these cases. Here we had introduced larger, because there are uncertainties in the long distance amplitudes, so therefore we varied them over the full range and tried to see the effect. And even, with larger and larger, of course your parameter space reduces, but at all this region here you are basically having deviations from standard model value. And in fact, we just go from minimum to maximum. We do find that even for the maximum possible long distance effect, the actual value of the polarization is different from what you get from the standard model value by many orders of magnitude. Of course, it is smaller, so whether that will be measurable is, of course, a question that the experimenters have to resolve. Okay, so as I said, in the experimental side, basically the photon polarization for B2S gamma was reported by LHCb. The photon polarization is obtained by the angular distribution of the photon direction with respect to the plane defined by the momenta of the 3 final state hadrons in the center of mass frame. So we could use a similar technique to look at photon polarization for D2 omega gamma. Omega, has a 3-body decay, so a similar technique can be used. And okay. And the branching ratios for many of these modes have been measured by the Bell collaboration. Of course, as I said, branching ratios, as long as they really are very well, enhancement is huge. And but even then, since the uncertainties with the long distance effects play a role, I would say it can be used as a probe, but may not, it may or may not be feasible. But on the other hand, as far as the polarization is concerned, that does help. That seems to survive for whatever value of long distance effects we have. And therefore, I encourage my experimental colleagues to look at the polarization. Thank you.
this nice discussion. So questions, comments? I'll start with Triporno. You had a question.